Sure. So this is a bit reminiscent of dark matter, actually. So we've been looking for dark matter now for really seriously, with massive experiments for a decade or so in terms of direct and indirect detection in space, gamma rays, deep underground direct detection, etc., and found nothing so far. At what point do we also get depressed enough by this and say, let's move on, let's change our theory so there's no more dark matter, we don't need it? I mean,
yeah.
Is that an option? How would you compare that with the...
Well, I think that's slightly different because, I mean, a smart new idea can always revolutionize things, and that could come along at any time, and you only recognize it in retrospect. Dark matter direct detection, it's not that whole classes of theory can be ruled out, but the experiments themselves will reach a wall because they're looking for events that are the collision of an invisible particle with a nucleus. And that can be simulated by invisible particles that we know exist, like the neutrinos. So another order of magnitude in the sensitivity, and they're going to hit the neutrino background. And then that will be that, because they'll start seeing events at a predictable rate that are kind of indistinguishable from direct detection of relic dark matter particles.
Well, unfortunately,
so
that's only going to be...
they're going to keep going
yeah.
until they reach that point, and then that whole area of experimental inquiry is, well, either succeeded massively before they reach the limit because they've actually got events, which of course could happen at any time. And I mean, thinking Bayesianly, if you ask me what did my priors say is the most likely next big advance in cosmology, I'd still say I'd put a reasonable amount of money on direct detection, because the model that the dark matter is a set of relic massive particles is so simple, and this expectation, if the cross-section of those particles is near what it is in neutrinos, that the density would work out right, the so-called WIMP miracle. That seems too good an opportunity for the universe to have missed. So wasn't it Steven Weinberg who said that the trouble with cosmologists is not they're always having crazy ideas, but they never take the simple predictions of the theory seriously enough? So the simplest hypothesis for dark matter is it's a relic particle, and so we ought to kind of expect that these experiments will find it.
No, I totally agree. We should push these experiments further. As you say, they're going to, in 5 or 10 years, reach the neutrino wall. But you have to remember, the problem is they're only looking in a tiny part of the dark matter parameter space. It's a bit like, you go for a walk in the woods and you lose your keys, and you go back there at night to look for your keys, and you just, wherever there's a lamppost or something, that's where you look, because you can't see anywhere else. So so in dark matter, there's a huge amount of parameter space that is going to be much harder to explore, but much of it can be explored. So I think the enthusiasm of our experimenters colleagues will, if anything, increase once they fail to find it in where they're looking now, in this limited mass range and parameter space range. Because there are so many other combinations of possibilities out there that...
but they'll have to start up with different techniques.
Yeah.
And they're going through the same kind of phase transition that astronomy is. I mean, it used to be that direct dark matter detection was quite simple. You just needed a piece of tabletop equipment you could build in a lab. Just a team of 2 or 3 people could do something and improve the limits on what the mass or the cross-section of those particles was. So it used to be cheap and easy, and so the field advanced rapidly. And then it's got more expensive, but somehow it's got a momentum that keeps driving it on to bigger and bigger things. Same in cosmology. People used to do galaxy surveys with a 10-person team. Now we're talking about thousands of cosmologists. So I think the natural way that what needs to happen is people have a smart idea of a new technique that, again, just a small number of people can exploit and make rapid progress, and with luck find something.
It's much harder in the dark matter community because the uncertainty in the dark matter particle mass ranges from, right now they're looking in the range of tens of proton masses to 1,000 proton masses. That's a factor of 100 dynamic range. This is where all these searches are that will run up with the neutrino wall in 5 or 10 years from the sun and from the atmosphere. But there are many theories out there where the dark matter particle mass can be, the smallest ones that are taken very seriously still that I know about are, we're talking about masses of 10 to the minus 30 the mass of a proton or something, some incredibly light things, tiny fractions of electron volt, or massive things that might weigh the mass of the sun, or even most recently 30 times the mass of the sun, whatever. Black holes, basically.
I know, wouldn't that be a completely serendipitous revolution if it turned out that the 30 solar mass event that LIGO saw was actually a collision between primordial black holes, as some people have suggested. Do you give any credence to that?
Not much, but the people that worked out the suggestion did the maths correctly, and they have to make assumptions like how you made the process by which you made the black hole was totally invisible. We don't see the energy release, but given that assumption, then they plausibly argue that once you made these black holes in the early universe, some fraction of them will be merging together today to give you the events one sees.
I think the concern is whether the black holes themselves would be merging with stars, for example, which so there's a concern about whether there should be X-ray flares and events like that we haven't seen. But people looked at these constraints quite hard, and I thought 30 solar masses was supposed to be in a hole. I must admit, I do find it surprising that we wouldn't have known.
It seems to be a window where one can hide things still.
Although again, that would then make it even harder to explain the approximate coincidence between... would it actually? If the primordial black holes were baryonic initially, then the approximate coincidence between the dark matter and the baryon density might make more sense, I suppose.
But that just indicates the huge uncertainty we have in the particle mass. If the dark matter is indeed a particle, which is not even necessarily in itself true. So at some point you have to decide, do we continue searching for dark matter, or do we put more of our effort into modifying the theories which gave rise to the existence of dark matter, that is gravity, Einstein's gravity. So that's an interesting decision. I don't know where you stand on that one. At what point do you switch your efforts?
Well, we were on this earlier on, weren't we? I think you need extraordinary claims, need extraordinary evidence. So given that we haven't seen a shred of it at the moment in terms of the large-scale studies, things like trying to measure the strength of gravitational lensing, which is a good probe of modifications of gravity, and seeing that the mass you infer for clusters from the light bending around it comes out consistent with, let's say, just adding up the mass that you can get directly, dynamically by motions within the cluster. That doesn't give me a lot of reason for wanting to put much time.
Yeah.
The best that you can say is that it's you can do these things anyway. So, for example, one of the tools that's necessary, essential now to interpret any of the modern simulation surveys is simulations, precisely because, as we were saying earlier, things are so non-linear on the small scales. You can't actually do analytic calculations that anyone will believe. So you've got to simulate these processes in detail. And when you're doing that, in a sense, it's not so hard to change the theory of gravity if you want to, if you're setting up all that apparatus. And so it's also a good thing philosophically. Even if you're Bayesianly certain that Einstein had gravity right, it's always a good thing to check if you can. So cosmology up to probably the turn of the century just took Einstein gravity pretty well for granted, applied that to the observations and deduced the consequences. It was only when some of those consequences, like dark energy, were quite radical, that people began thinking seriously, were we sure of our premises? And even if you were sure, well, it's nice that you can actually test it rather than just having to take it as an axiom. So the only question then is at what price? Is it worth $1 billion to test something that you're pretty sure is right?
So this sort of gets you back, suppose you're a graduate student, a beginning graduate who comes to you and asks for advice on what he should do his PhD in. And he offers you the choice of, modified gravity or dark matter, experiments, or logical structure or galaxy formation. I mean, you would have strong, prejudice to which of those directions to take, would you?
Yes, but I think they would be instrumentally based. Despite all the wealth of ideas that people inject, in the end, cosmology has been driven by technological developments that let us look at the universe in a new way. Don't you think? There's been a lot of serendipity. So even if you're a theorist, it's hard to be a pure theorist these days because you're in the business of interpreting what the telescopes deliver. So you should look long and hard at where the next technology jump is going to be. You already talked about 21 centimetre. So I think, I would be tempted to start from where are the radical new data sets going to be and which areas of science do they bear on, and then get on in there.
So
and the trouble is that they all tend to be big team science, so you're finding a little piece of unexplored territory that you can just go off and play with was once possible.
Well, one could still do
so easy. If it was easy, I wouldn't tell a student how to do it, I'd do it myself.
Right. Well, one could still do the theory. I mean, the big teams do the experiments. So there's one obvious region now that is about to boom dramatically, and that is gravity wave detection. I mean, that is just a whole new window on the distant universe that's beginning to open up. I think that would be one of my prime suggestions for someone beginning research.
The trouble is you always want to go back in time. Right? I mean, the great advice is get into gravitational waves 10 years ago. Similarly, in 2010, you just said, get into exoplanets about 2000. So maybe in 10 years' time, I'll know what I should be advising the students now. Except that,
it was a big surprise to me with the discovery just a few months ago from Advanced LIGO of the merging 30 solar mass black holes, that this merger occurred, it's occurring now, but the formation of the black holes occurred in the very early universe, because they could only have formed from relatively metal-free host stars, precursor stars.
Yes.
And so suddenly, and what is more, one can even get distances from the gravity wave measurements to these objects. So, we've just had one or two events so far. So it's clear that as this whole experimental field develops, with hundreds and hundreds of new events a year, we'll have a whole new way of doing cosmology, basically. So to me, that's very exciting. I see a whole new window opening up there.
And it was kind of predictable. I think that this first event, as far as one can tell, they probably got a bit lucky. But there was a technology curve of increasing sensitivity.
Yeah. But the cosmology
about now should have delivered something.
That's right.
And that's why a lot of people, when I read the gravity wave papers, they read very much like cosmology papers, and you can see that there are people who kind of jump ship from from standard astronomy, but bringing the same kind of statistical approach with them. So,
but I think all the people that worked on this for 10 years and were making predictions were focused not on mergers between massive black holes, but more modest events.
Neutron stars,
exactly.
And those things will come.
And so it really was a surprise, to the cosmology community, I think, what happened. A very, very healthy surprise, actually.
Yes. But it's been a while since we had a self-generated surprise like that. Some people present the discovery of the accelerating universe in that way. Coming back to lambda and fine-tuning. But my perspective was that the evidence accumulated much more gradually than that, and certainly large-scale structure, CMB, or even CMB upper limit non-detections, really paved the way where we were largely convinced that there was a vacuum energy before the supernovae. Would you agree with that?
I think so. Basically, the budget of the universe, the mass energy density budget, was forcing you to that conclusion. That is, if the universe was spatially flat, more or less, and you'd only had 1/10 of its critical mass energy density in matter, otherwise one would get excessive velocities of distant surveys, etc. There had to be something to bridge the gap, and I think there was a consensus forming towards vacuum dark energy before the, if you like, the formal discovery.
Yes.
So it wasn't such a surprise. It's more of a confirmation of prejudice for many people, I think.
Yeah. So when I take that kind of historical point of view, it would be nice if there were other things in cosmology where you could kind of feel the field congealing, or at least a suggestion that we were being pushed in a certain direction, even if the evidence wasn't statistically compelling yet. But it seems to me that there's not too much of that. And we have this standard model with 6 or 7 parameters, and it works extraordinarily well.
Mm-hmm.
But some people always like to focus attention where there's a tension between 2 different experiments at the 2 sigma or so on level. But it seems remarkable to me that there's nothing more indicative than that.
So maybe it's, worthwhile advice would be to focus more on galaxy formation or some structure evolution rather than the structure itself, and the physics of how that evolves over time.
But then that's just accepting that the framework is converged, that we're going to have those same set of parameters, and that we're just going to, in 100 years people will still be arguing about whether they're fine-tuned or not.
Yes. It's hard to see an alternative, actually, isn't it? To that, don't you think?
Yeah, if I had to guess, I would guess that we've converged.